So welcome everyone. Today we're having a talk from a great friend, Stefano, who's an associate professor at the University of Turin. Before that, he was a postdoc at Institute Superior Technical in Lisbon, and after that, he was a postdoc also at the University of Manchester. And he's going to talk to us about cosmology with the SKA Observatory. So yeah, please take it away, Stefano.
Thanks, Shahab, Will, and everybody who is there for being here and for inviting me for this seminar. I've been told you will be having pizza at the end of the seminar, which is a pity because I won't. And the time scale would have been perfect for me for like some nibbles before dinner, but I'll try and catch up in another way. So today I'll be talking about cosmology with the SKA Observatory, which is topic that I'll be presenting also on behalf of the Cosmology Science Working Group, which I've been chairing for a couple of years now. But in general, for most of my career, I've been interested in cosmology across wavelengths and with possible cross-correlation and synergies. So I will have some of these things creeping in my presentation. And there's also why I know Will and Shahab and other people also very much involved, not just in SKA, but in Newton. So, but talking about the SKA, so let me put my SKA Observatory hat on. Talking about the SKA, I want to tell you a few things because this is a new being, if you want. So the SKA Observatory, as an intergovernmental organization, was born rather recently, on 15 January 2021. And it's the second intergovernmental organization for science in the world. But the process that led to the creation of the SKA Observatory has been a long one, almost 2 decades, and started back. So in this slide here, you can see the major dates that marked the creation of the SKA Observatory. One of them being basically the signing of the convention for the creation of the SKA Observatory in Rome in 2019. After that, there's been a couple of years of ratification by process by different parliaments, and when the quota of 5 countries has been secured, it was by the end of 2020. So basically, the observatory could have been born. At the moment, this is like the situation in terms of member countries. I'll go back to this later, but the SKA Observatory is a rather peculiar one because it will be built into sites in South Africa and in Australia, as you see here. And there's like the global headquarters that are in Jodrell Bank in Manchester, well, near Manchester in the UK. But member countries are spread around the world. Canada is one of them, most countries in Europe, Australia, South Africa, of course, India and China. And like here, it's partly covered by my face and your faces, but on the right-hand side of the slides, you can also see like what are the countries that are interested in joining, and those marked by an asterisk are those that have already joined. There's already, I mean, this is already out of date because, for instance, as far as I know, France has joined too, so there should be also an asterisk there and others. Also, there's a part of African countries that are involved in the SKA to develop radio astronomy in Africa. From the point of view of the SKA project, so the SKA, which was formerly known as Square Kilometre Array, now the spelling out of the name doesn't exist anymore. SKA is just SKA. But the point is that it will be the largest radio telescope on Earth when it will be built. It will be built, as I was saying, in 2 locations, South Africa and Australia, and it will be composed of 2 different instruments in the sense. It will cover a range between 50 megahertz up to 14 gigahertz, with a goal much larger than that, up to 20-something gigahertz. And the 2 instruments will be covering different bands of this very wide spectrum. In particular, the so-called SKA low instrument is the low frequency instrument covering between 50 and 350 megahertz, and it will be composed of antennas spread in Western Australia, in a desertic area, because you want to avoid as much as possible interference with other radio sources. And it will be constituted by about more than 100,000 antennas spread in total collecting area of almost half a kilometers, with 65 kilometers between maximum distance between stations. Yes, was a question? No. If you want to compare that to the best similar instrument in the world as of now, that is LOFA, the low frequency array in the Netherlands, and SKA low would be 25% with better resolution than LOFA, 8 times more sensitive, and more than 100 times faster in scanning the sky. On the other end of the spectrum, with SKA mid instrument, that is what is being built at the moment in the Karoo Desert in northern South Africa, and that will cover the range between 350 megahertz all the way up to more than 15 gigahertz. It will be composed by about 200 dishes, so these are not antennas, these are parabolas, and the total collecting area will be about 33,000 square meters, with a maximum distance between baselines of more than 150 kilometers. Again, if you want to compare this to the current best similar instrument in the world, that is the Jansky Very Large Array, the SKA1 mid will be 4 times better resolution, 5 times more sensitive, and more than 60 times faster in scanning the sky. In terms of science, well, that's an observatory, it's not an experiment like Euclid if you want to compare. So it will not be just doing one thing, but it will cover a wide range of science cases as well. These science cases are mostly, well, in the radio, and they cover from cosmic dawn and reionization, cosmology, galaxy evolution, pulsars, cosmic magnetism, and the cradle of life. These science cases will be split between the two instruments, with SKAO's low telescope being mostly focusing on the detection of cosmic dawn and reionization in the range between 50 and 350 megahertz, whereas the other science cases will be mostly covered in by SKA 1 mid. For cosmology, what will be interesting for us is mostly the so-called band 1 and band 2 that are shown here. So between 350 megahertz up to 1,760 megahertz. If you're interested in SKA Observatory science, I can advise you these very handy books. These tomes, these massive tomes, are actually the proceedings of a conference that was held in Sicily in 2014, to the aim of like reappraising science, SKA science after some time. So this is not, these proceedings will not cover only cosmology, but all kinds of science that I've been talking about, I've been mentioning. But if you're interested in cosmology, there's something else that I'll mention later. Again, in terms of science, the major dates are, well, construction started in 2020 and between 2020 and 2021, and these are the major dates that you want to keep in mind. And this rather busy graph shows you what are the science milestones that have been proposed as a function of the date. So with some major science meetings ongoing for all this time period, on the right-hand side, top right, you see like the KSP proposal, so the key science project proposal, which are the real survey for science that we aim at doing, particularly for cosmology. And this will start in the second half of the 2020s, so with a good commensality with other cosmological experiments like Euclid, LSST, and similar. I was saying, in terms of, if you are more interested in terms of cosmology, there's an updated text that you can look at compared to the 2014 proceedings. This is what we called the SKA Cosmology Red Book 2018. So we like borrowed jargon from European Space Agency, space missions. So the Red Book is meant to be like the reference text for a mature experiment. And in this text, you can find basically technical specification and performance forecasts, the most up-to-date that you can look at for cosmology with the SKA. Roughly at the same time of this paper, another came out with a slightly unfortunate, very similar name, which is Fundamental Physics with a Square Kilometer Array. This text was the proceedings of another conference, and this deals with a bit more futuristic also settings of the SKA. But if you're interested in also other types of fundamental physics, not just cosmology, you can have a look at this paper as well. But now, for the rest of my talk, I would like to focus on what is the kind of cosmology that you can do with a radio instrument like the SKA, what is different and what is complementary to optical surveys, and also draw some possible synergy that can be done. So in terms of surveys that can be carried out on these radio wavelengths, there are mainly 4 of them. So 3 are more traditional to optical surveys, and 1 is very peculiar to the SKA and radio surveys. On top of these, of course, there are all the multi-wavelength synergies that you can think of. But in terms of traditional surveys, let's say there are galaxy surveys. One of these is H1 galaxy surveys or continuum galaxy surveys. Then we have radio with lensing. And finally, there's the most peculiar one, which is H1, so neutron hydrogen intensity mapping. And I'll go through them, each of them separately, just for you to describe them properly. Let's start with the most traditional one, if you want, H1 galaxy surveys. The origin of, this kind of measurement is the 21 centimeter emission line of neutron hydrogen in galaxies. So, as you know, neutron hydrogen emits photons of 21 centimeter wavelengths in rest frame. This is a forbidden transition because it's the hyperfine split of neutron hydrogen, but being neutron hydrogen the most abundant element in the universe, there's so much of it that you can actually detect this forbidden transition. So basically, at these wavelengths, at radio wavelengths, we have this 21 centimeter line, which is very recognizable. And the idea here is doing like a mission line galaxy survey, much in the same way as H-alpha galaxies for Euclid or ELGs for SDSS and DAISY. The main pros of such a survey is that you have spectroscopic redshift accuracy, so you can really map galaxies 3-dimensionally in the universe, and you can also have information about peculiar velocities, which can come up very handy. The cons are the fact that there are few galaxies. This is a faint signal after all, and is a threshold experiment. So you're basically throwing away some of the information because you don't need the threshold in terms of flux detected. Some examples of H1 galaxy surveys are high-pass and alpha-alpha. Both of them detected galaxies rather locally, which is the reason. This is because, as I was saying, H1 is a faint signal, and so usually this kind of survey has not been used for cosmology, at least not as much as other optical surveys. But these things can change with the SKA. One of the most interesting things about this kind of survey, in my opinion, is that they can be so-called Tully-Fisher survey. This is because the intrinsic luminosity of a galaxy that you can get from the 21 centimeter line width, combined with the measured redshift, can give you can allow you to infer the peculiar velocity of the galaxy. So basically, at the same time, you have 2 traces. You have galaxy positions and peculiar velocities. And this is very nice because then you can try to measure separately the power spectrum of positions, power spectrum of peculiar velocities, or the peculiar velocity divergence, which is here denoted by U, and the cross correlation. In this plot, which is in a paper almost like 20, wow, that old, really? Okay, anyway, you see the fractional error on growth, F sigma 8, that you get as a function of the maximum redshift that you include in your survey when you use galaxies only, which is the red dashed curve, when you use peculiar velocities only, which is the green dotted curve, and the cross correlation, which is the purple dotted dashed curve. So basically, as you can see, at low redshift, peculiar velocity is very useful because they can provide some information that is not, the galaxies are not able to provide, galaxy positions are not able to provide. And if you follow the blue curve, denoted by 2 fields, which is basically means the multi-tracer of this, basically you can gain more than just the sum of these things because of all the mutual cross correlations. With a student of mine, Agata Marazzina, currently looking at what this would mean in terms of measuring the growth index. So for modified gravity, growth index gamma equals to almost 0.55 for general relativity. But if it's different from that, you can it's a possible hint of modifications to gravity. And here you see just a one-dimensional profile likelihood, well, the delta chi-square for the measurement of gamma from galaxy in an SKA H1-like galaxy survey, which is in blue, the peculiar velocity one in yellow, and the cross correlation in green. As you can see from this plot, you get that most of information on gamma is contained already in the galaxy power spectrum, but there is an interesting follow-up of this. So in this plot, sorry, the y-axis labels is wrong. This is just the error, the marginal error on gamma. Well, the ratio between the marginal error on gamma that you get from the cross correlation between peculiar velocity and galaxies to the one that you get from galaxies alone, and as a function of the fractional velocity error of your survey. So this is a quantity that depends on how well you can measure velocities in your survey, and the current value that is assumed for similar surveys is about 0.2, so in the ballpark between 0.2 and 0.25. But in principle, you can get better measurements, and as you can see, there's a sharp transition when you get to values that are smaller than 0.1 something. And this is due to the fact that the total error that comes into the measurement, the power spectrum of peculiar velocities, has a contribution from this fractional velocity error plus some random motion of galaxies. And when you get basically to the level of having only this random contribution, basically you can gain and be as good as just galaxies alone. So this is worth being explored. This is what we're doing at the moment. But if you don't have any question about H1 galaxies, I'll move on to talk about the continuum galaxy survey. Here, the idea is that you detect galaxies through the synchrotron emission due to charged particle within galaxies. The pro of this is that it's a strong signal, so you have a large number of galaxies, but unfortunately, you have almost no redshift information. And this comes from the fact that continuum is just, well, synchrotron is mostly a power law, so that you don't have any spectral feature that can allow you to know what is the redshift. So redshift and flux are degenerate. This implies that in continuum galaxy surveys, you cannot do the usual Fourier space or three-dimensional correlation function studies, because you don't know where the galaxies are on the line of sight, but you have to rely on harmonic space power spectra like CLs or two-dimensional correlation function. So some of the information on the line of sight is in principle is wasted, is not included unless you do some tricks like identify galaxies with other surveys, etc. Example is this of VLA first that detected about 900,000 galaxies over 10,000 square degrees, and XPSS, of course, which is the most famous one, which detected about 2 million galaxies with also Stokes Q and nu polarization maps over more than 3/4 of the sky. But a more recent experiment that I'll be talking about later is related to one of the SKA pathfinders, and is the RAX survey, which detected about the same number of galaxies, sorry, more than MVSS's galaxies, so 2.5 million galaxies over a slightly smaller area. And there's much that can be done with this. With continuum galaxies, you can do things that you usually do with continuum galaxy surveys, so studying like cross correlation with other surveys, etc., or studying non-Gaussianity. But something that I thought is interesting because it's different compared to what you do with other surveys, is testing fundamental hypotheses in our understanding of the universe, like the cosmological and the Copernican principles. So the assumptions that you usually have is that there's a preferred rest frame and comoving observers, which are us, and there's this rest frame, this preferred rest frame is the same at all different redshifts, and is the same for all probes that you can use, so CMB and different galaxies, galaxy traces, let's say, well, traces of the Vasquez structure. But the questions that you can ask yourself is whether the CMB is due to just a kinematic effect, and what about other dipoles of the Vasquez structure? You can ask yourself whether we can establish a cosmic rest frame. Can we link dipoles to local structures like great attractors, bulk flows, and things like that? or can we measure non-kinematic contribution to the particle? And in continuum galaxy surveys, they are particularly well suited for this because in this graph in this cartoon that you see on the right-hand side, you see the difference in the volume of the universe that can be probed by a continuum galaxy survey like with the SKA over 3/4 of the sky compared to BOSS and to Euclid even. And the reason for this is that in the radio, you don't have dust obscuration. So the distribution of galaxies over redshift that you can detect, even though you don't have that redshift information, but still you can detect galaxies at much higher redshift. So you have a higher redshift tail for those galaxies. And this allows you to really probe huge volumes of the universe. So in terms of this, SKA Observatory will have a continuum galaxy angular correlation function that will be able to detect, given forecasts, the dipole of the last case structure within 5 degrees of error bar, let's say, with the SKAO, and even within 1 degree with the futuristic setup for the SKA Observatory. Yeah. Okay. If there are no questions on continuum galaxies, let me move on to intensity.
Well, so just to ask about that dipole, so this forecasted accuracy, is that for the the amplitude of the dipole that's expected just for
the amplitude? Yes. No, sorry. Within 5 degrees is the direction of the dipole actually.
No, I understand. But presumably the precision, of this direction depends on the amplitude of the dipole, right?
Sure. Yes.
Right. Yeah.
Yeah.
Right. So my question just is, whether the assumed amplitude is that given, just by the normal power spectrum.
I think that in this, so the references are there for this analysis. From what I remember, these were done assuming that the amplitude of the dipole was consistent with that of the CMB, which is actually not always the case in radio surveys. So one of the things that we also would like one of the questions that we'd like to answer is whether the amplitude of the dipole is consistent with the CMB or not. Because with other galaxy surveys in the radio, like for instance TGSS, we find an amplitude for the dipole which is significantly larger than that of the CMB, and the tension is at a few sigmas. Mm-hmm. And this is not explained, so this is something definitely we would like to understand better.
Okay, great, thank you.
Thank you for the question. Then let me move on to intensity mapping, which is like the really like the new thing in this context. The origin of the idea of having these intensity maps of neutral hydrogen is that basically you can do map the integrated emission of 21 centimeter photons in galaxies after the end of reionization, under the assumption that after the end of reionization, most, if not all, of neutral hydrogen is contained within galaxies. The pros are that no photon is lost, so you don't waste any photon because this is not a threshold experiment. And naturally, and we see that, we can have better than spectroscopic redshift accuracy. But unfortunately, you trade the radial accuracy with angular resolution, at least with single dish experiment, not with interferometers. And the real elephant in the room is that the foreground contamination is far to be well addressed at the moment. Examples of this are, the first measurement of this has been done with the Green Bank telescope over 1 square degree in cross correlation with Wiggles at redshift between 0.53 and 1.12 by Tsuchin Chang and others in 2010. And more recently, over much larger area of the sky, thanks to the cross correlation between GAPT and EBOS on top of Wiggles in this paper by Lara Woods in 2021. Roughly at the same time, after this new interest in intensity mapping, a much more local measurement of the cross correlation with between galaxies from the 2 degree field galaxy redshift survey and parks in Australia has been done. And the last two are the real new elements here, because the penultimate one is the cross correlation between Wiggles galaxies and Meerkat, which is one of the SKA pathfinders. And and Meerkat represents the first single dish mode measurement of the cross correlation of intensity mapping. So where you use an array of dishes, like each of them was just a single dish and not using the cross correlation. And CHIME is, well, is the Canadian, you know that much better than I do probably, the Canadian intensity mapping experiment, which is an interferometer, is built to be an interferometer, is a rather peculiar shape, it's like this series of cylinders. And they detected, it's not really detection of the power spectrum, but still the cross correlation, sorry, but it's a stacking, which is not much different in a sense. And they managed to have a detection with stacking fields of these intensity maps against EBOS, luminous red galaxies, ELGs, and quasars at quite high redshift. The idea of intensity mapping is just the following. Instead of having a threshold experiment with detect galaxies at a threshold, you integrate the whole emission of those galaxies. And basically, where you see a lot of emission, which is in the Rayleigh limit, is just a lot of temperature. It means that you have a lot of galaxies in that pixel. Whereas, sorry?
Can you hear us, Stefano?
Yes.
Yeah, you can hear us good. Okay.
Oh, sorry, Stefano. I was just having a question on what the statistical significance is of these different detections that you had in the previous slide.
So all of them are real detection in the physics sense, in the sense that are above 5 sigmas or about. But I just listed the references there because I don't have the numbers on top of my head.
Okay, no worries. Thanks.
The other thing that I wanted to say when I mentioned the fact that you have better spectroscopic accuracy is that with this kind of intense experiments, redshifts come from free, because you're really using a radio. You're tuning your radio to detect a given frequency, and that frequency is the redshifted frequency of neutral hydrogen, which in the rest frame is 21 centimeters, so 1 gigahertz point 42. So basically, the channelization that you can reach is about of kilohertz, meaning that you get errors on redshift which are ridiculously small. So basically, you can have like really a lot of slices, more than you can actually deal with. So usually, you also bin them later. The idea, well, what could we do? For instance, from the point of view of astrophysics, we could map the abundance of neutral hydrogen in the universe across redshift. This is a quantity which is peculiarly poorly known, as you can see in this plot, where the colored arrow bars show the measurement that we have at our disposal at the moment, which are not really, well, they are in agreement, sort of, but still there's something that needs to be understood. And the black points are measurement, well, forecasts for measurements from the SKA. You can wonder why the arrow bars for the black points change in shape at a certain point, and this is because we are crossing 2 different bands. So we're using 2 different bands on the instrument. Other things that you can do with intensity mapping from more of a cosmological point of view are resumed in this couple of slides. This is a busy plot, so let me guide you through it. What you see here is the noise to signal ratio for the measurement of the power spectrum at a given scale, which is about the BAO scale. So K equals 0.074 inverse megaparsecs as a function of redshift. If you want to compare something which is like state of the art for the coming future, so Euclid, H alpha galaxies, that's the black line that you would have to look at. So between redshift 1 and redshift 2. And if you want to compare that to SKA, sorry, I don't have the pointer here for some reason with sharing of the screen, so I cannot point you, but this is the black curve. This is Euclid. And if you want to compare that to an SKA like intensity mapping experiment with MID, that would be the gray-blue curve, which is just about above the red one. So as you can see, it reaches the same kind of sensitivities that Euclid, a slightly smaller redshift, that's nice, but then it increases very much, so it's not competitive with Euclid in that range. Nonetheless, if you look at BAOs, in this plot here, you see what could be done is a comparison with Euclid to detect the wiggles with an SKA-like and some precursors. And it means that it's not that bad anyway. But the real game changer in terms of intensity mapping for cosmology is when you look at sorry, other scales. This is the same plot as before, but a much larger scale. This is 0.01 inverse megaparsecs as a function of fraction. Now Euclid is the same line as before, is the black one, whereas the blue, the solid blue, is SKA mid. And here you see that basically you have you can reach scales that are not allowed by standard galaxy surveys with intensity mapping, because you can probe much larger volumes. And this is particularly interesting, this sensitivity to ultra-large scale effects, which are, for instance, the possibility of detecting signatures of non-Gaussianity, primordial non-Gaussianity, which will be important for inflation, studies of inflation, and also the possibility of detecting relativistic so-called light cone projection effects, so correction to the clustering of galaxies in the standard like Newton plus Kaiser limit that come from the full treatment of relativistic perturbations. And like probing, detecting such effects on very large scales may be like the first real detection of relativistic effects on cosmological scales, not on like in the very, 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 very weak regime, not on strong gravity regime. So this is important also for modifying gravity studies. But as I was saying, the elephant in the room. Yep.
Stefano, can you remind us, so SKA 0 mid B1, SKA 1 mid B1, and so on. What are the timescales again for these 4 different scenarios?
Yeah, so you should look at SKA 1 mid solid line B1, which is band 1, because it's what is being built. This paper, well, these plots from this paper come from a paper by Phil Bull and this 2014 proceedings that were actually published in 2015. But we're also referring to so-called SKA 1 SIR, which was supposed to be the Australian contribution to the cosmological surveys. But that has been descoped, so that bit is not going to be built in this current construction of the SKA. So basically what you want to refer to is the solid blue-ish, like azure line that you see there. Same for all these lines that you have here.
And to which extent is this dependent on being able to control the foregrounds? So to which extent would these lines shift up and down depending on the foreground mitigation?
Well, more than shifted up and down is really that foregrounds are going to affect primarily, unfortunately, the larger scales, at least in autocorrelation. So you definitely need to know them well, and you may have to remove some of those large scales. You cannot really trust your foreground, like avoidance or foregrounds decontamination procedure. And this is what I was going to say about this slide. This is courtesy from Richard Shaw, that shows you like the extent of what we have to face, the challenge we have to face to make intensity mapping really competitive with on these scales. And the fact is that, well, if you think of CMB, there's the issue of foregrounds there as well, but the signal and the foregrounds for CMB experiments are about of the same amplitude. Whereas in this case, we span many other orders of magnitude. So in the left-hand side of this plot, you see the like simulation for the unpolarized foreground, and then there's this stripe, which is zoomed in the bottom left, and they show you, like, you see the galaxy, and this is mostly synchrotron in terms of unpolarized foreground. And the amplitude of this in terms of temperature related to the intensity, the brightness, temperature brightness, is of order some 100 of kelvins. Now, if you look at the polarized programs, which are very nasty, that you have to control as well, you see here that the scales are a few kelvins. And then if you look at the right-hand side, where you have 21 centimeter signal, which looks very, very random because it's due to the fluctuations like CMB, if you want, we're looking at hundreds of microkelvins. So basically, we span like 3 to 4 orders of magnitude between the signal and the foregrounds. This is a huge challenge that we have to face. There are facts that allow us to face it, and for instance, is the fact that foregrounds are smooth in frequency, whereas the cosmological signal is almost random in frequency. So there's the possibility of like fitting for them, but like template fitting is not something that is really thought of anymore at the moment. Much more refined techniques are under study. like, well, principal component analysis, everyone knows that, but also other techniques in this sense. And this is where most of the effort at the moment is ongoing for intensity mapping, like with the pathfinders. Let me move on to the last of the 4 surveys that I listed for cosmology with the SKA, which is radio weak lensing. Well, radio weak lensing is just weak lensing as you do with galaxies, but measured in the radio. It's complementary to, well, we know that it's complementary to clustering and sensitive to galaxy biases, but it can also be complementary to optical shear surveys, which is why we want to do that. We know that it's low signal to noise, at least at low redshift, it increases with the redshift. And the thing with the radio is that the question we haven't answered yet is whether we need imaging. So we need to, I mean, interferometers look at the Fourier transform of the sky. Do we have always to anti-transform so that we can actually see galaxies, measure them, their electricities, and then compute the power spectrum? Or can we do that directly in Fourier space, which will allow us like to bypass this Fourier transform and have a completely different kind of measurement for shear? This is an open question. But examples of this has been the first and only detection at the moment, as far as I know, with VLA first in beginning of the 2020s, sorry, in the 2000s, and many other cross-correlation detection with other optical shear surveys or galaxy clustering and cluster surveys, always with VLA, sorry, and other optical radio surveys like Merlin, SDSS, and Cosmos. In terms of why this is interesting, here let me show you this plot. So here you see the source redshift distribution. So the N of Z as a function of redshift for an optical survey like dark energy survey, 5,000 square degrees, and SKA1 like continuum surveys for weak lensing. You see that the shapes of these distributions are very different. In general, in the radio, you have fewer galaxies, but you can reach to a higher redshift, I will say, because you're not obscured by dust. And this is the reason why you have this long redshift tail with the black histogram compared to the pink one. This translates to like some really nice complementarity when you look at the power spectrum. So these curves are the tomographic cosmic shear angular power spectrum as a function of angular multiple, which is of course like the dual of the angular scale. And so large N's are small angular scales and small N's are large angular scales. The color code is the same. DES, so optical, is in pink-ish, and SKA, so radio, is in black. So this plot tells us two basically main, I mean, there are two take-home messages here. So all these different curves are due to the fact that we can do tomography, so we can look at auto beam correlation and cross beam correlations. And in general, due to the fact that lensing is an integrated signal, and the further the galaxies are, the stronger the lensing signal is, reflects in the fact that the pink curves that are related to optical, which is more local, are usually smaller in magnitude than not the black ones. So radio sources reach out to higher redshift, meaning that you can have a larger signal. On the other hand, we have fewer sources in the radio, meaning that the shot noise becomes more important, at least at larger scales. And this is the reason why the error bars for the radio survey are larger than from the optical. So this shows already like a nice complementarity between the two. Another thing which is really cool then is the following. So when you measure shear, what you do is correlating ellipticities of galaxies, epsilon. So the measured ellipticity, the observed ellipticities at a given redshift and as a function of a position on the sky, you can think of it as a sum of like the cosmological signal gamma that you are after, plus some systematic effect that you have to remove from the data. Now, when you take the power spectrum, you basically take the correlation between two ellipticities, you end up with the correlation of the cosmological signal, which is the power spectrum of shear that you want to measure and compare to your theory, plus the cross correlation between the systematics and the cosmological signal, which in principle, I mean, unless the universe is really nasty, should disappear, should decouple, and the power spectrum of systematic. Meaning that you really have to know your signal very well if you don't want to infer a wrong a spurious power spectrum due to the presence of this systematic. But now if you do the same exercise, measuring the ellipticities in the optical and in the radio, like with Euclid, say, and SKA, you end up with this sum, where the cosmological signal is the same because lensing is achromatic, doesn't depend on wavelength, it's always the same. Then you have the two terms between the cosmological and the systematics, but they should both disappear. And finally, you have the cross power spectrum between systematics in the optical and systematics in the radio. But these are two completely different experiments. Like one is an interferometer, the other is an optical telescope. And so they don't have anything to do with each other. And in principle, then they should also disappear. So by looking at this cross correlation, you can have a pristine measurement of the actual cosmological signal. This we showed in a series of papers when I was in Manchester with Michael Brown, Ian Harrison, and others in Manchester. And just to show you an example of this, in this plot, you see the 1 sigma contours on the measurement of dark energy parameters, W0 and WA, for radio surveys in red, optical surveys in blue, and the cross correlation in green. And well, the cross marks the input of the analysis, or what we want to recover from our forecasts. And you can see that all the ellipses are roughly of the same size, meaning that, I mean, the different colors are the same size, meaning that the information contained in the optical and the radio and the cross correlation is about the same, which makes sense because the signal, I mean, they're not different traces, they're actually the same signal. So it's exactly the same thing. But then you see that the colors, so the red and blue ellipses are shifted around. Some is centered in the right place and some is not. And this is because in this analysis, we also allowed for some like systematic effect not included in the treatment then of the analysis. So basically we injected some extra signal that we didn't model when we fit for the parameters. And what this plot tells us is that you don't really change the precision of your measurement, but there's an issue with accuracy, because you can think of measuring like some non-zero dark energy parameters, so not lambda CDM, but actually this might be due just to the presence of systematics. And this instead is not the case for the cross correlation, just because of what I told you. So the fact that the cross correlation is not affected by these additive systematics. Then let me skip one slide just because I'm running short of time, but towards the SKEO, it will take some time, but luckily we have plenty of experiments that are ongoing. They are split between precursors and pathfinders. Precursors are experiments that are located at future SKA sites, South Africa and Australia, and Australian are already taking data. Pathfinders are experiments or instruments that are engaged in SKA-related technology and science studies and can be used to test pipelines and things like that for the SKA as well. It's already 1/4 so I have a few other slides that talk about like some results that we already have for 3 of these pathfinders, but please let me know whether you want to go on with the questions, or it's okay if I keep talking for another like 5-something minutes.
Yeah, I think 5-6 minutes is good.
Right, cool. Okay, I'll cover at least some of them. Given that I started talking about continuum surveys here, let me go with the ASCAP, which is like the Australian SKA Pathfinder, and ASCAP is the one that is the instrument that did the RATS, so the Rapid ASCAP Continuum Survey. So this is the deepest radio survey of the southern sky today, at least at these frequencies, Citron frequency of about 900 megahertz. And thanks to its largest instantaneous field of view, which is about 31 degrees, it was able to, with 900 pointings of 15 minutes observation each, to cover the entire southern sky up to 30 degrees latitude north. So about 3/4 of the sky in about little more than a week. This is amazing because it allowed this for observation for the deepest radio survey in the southern sky. So this was not meant to be for science, it was just meant to be for the fun of having the possibility of doing this. But actually you can do science with it. And with this 1 million galaxies, when you cut out the galactic plane at ±5 latitude, you have a catalog that you can use for your studies. And this is what we did, for instance, in this paper led by Benedict Barkalus and with David Parkinson, Catherine Hale, and others last year, well, this year. So where we measured the cross correlation between RAC galaxies and the symbiote temperature. Here you see the cross, you see the cross correlation power spectrum in harmonic space, CLs, between galaxies and temperature as a function of multiple. You see the data and you see the model with no ISW and the relative error bars. And this allowed us to measure the integrated Zatz-Wolf effect with the detection, like with this significance. So we measure the amplitude of the ISW effect, that should be 1, with these error bars. So this was just to show that it was possible to do science with rats and to test the pipelines that we have for continuum galaxy surveys with the SKA. Another one that I would like to mention is Meerkat. Meerkat is the pathfinder to the SKA in South Africa. And some years ago, with Mario Santos, who is the PI, we proposed MeerClass, which is the Meerkat Large Area Synoptic Survey. And the aim is to do H1 intensity mapping and continuum cosmology with lots of condensalities between different experiments. And we want to focus on sky patches with multi-wavelength data from mainly for cross correlations. This is done, well, this is proposed to be done in the so-called L band between 900 and 1.7 roughly gigahertz, which corresponds to redshift smaller than 0.58. So this is the proposal that was put forward. And in the proposal, you can see the idea of the detection for baryon-acoustic oscillation using intensity mapping with a 4,000 hours of observation at 4,000 square degrees survey. We weren't allocated this just after the proposal, so that's why we proposed a rescaled version, which is what you see here. These are the forecasts for that. This is only 18 hours over 200 square degrees of covering the same patch of Lyle's wiggles. You see the error bars, and the central redshift of these new proposals is 0.28. This has been observed, actually. You see this paper from last year by Jingying Wang, where it showed, you can see that like the maps of temperature, this is no foreground removed, nothing. It's just the temperature of the sky and that frequencies. And you can see overplotted these purple dots. These purple dots are known point sources. And you can see that like the bright spots in the map nicely correlate with the position of these bright spots. So this has been used to also with foreground removal techniques to obtain like cleaned maps that have been then cross-correlated with Wiggles galaxies in this redshift range. And this led to this detection of the cross-correlation by Steve Cunnington et al. So the first cross-correlation measurement done with intensity mapping with single dish mode for the SKA, for like SKA Pathfinder in cross-correlation, as I said. And here you see the data that allowed to put at least a limit on the total amplitude of this power spectrum, which is proportional to, well, the bias of neutral hydrogen and the total abundance of neutral hydrogen at that redshift. And in this plot, you see like some of the consistency tests where, for instance, the blue points are the same points as before, but the red one are what you get if you shuffle the Wiggles galaxies, and as you expect, you don't see any cross correlations. With this, now we have new data from Meerkat, and we aim at doing this again. And well, of course, the goal is the detection in photocorrelation. Let's see if it happens. And really, yeah.
Question: what is no TF?
TF is transfer function. So it was a method that was applied in this paper to do the detection. So to correct for over cleaning due to the foreground cleaning techniques.
Okay, thank you.
You're welcome. Finally, just one word about radio with lensing. So this is not a pathfinder, but it's a precursor. Sorry, the other way around. It's not a precursor, but it's a pathfinder. It's eMerlin, which is the interferometer in the UK. And with the Merlin, at the time I was in Manchester, there was this project ongoing that is still ongoing, which is a super cluster assisted shear survey, superclass. The idea of this is to pave the road to detecting cosmic shear in the radio band. And at the moment, at the time of that publication in a couple of years ago, so the first superclass overview and data release, number densities and areas were very small, but at least it allowed us to test the pipeline. So the surface density of galaxies was about 0.1 galaxies per square minute, covering a quarter of square degree. Here you can see the map that was covered. It's called supercluster assisted because the idea is that we wanted to focus on an area of the sky with a lot of superclusters. You see 4 in the northern side of this this map and 1 below, and the presence of this huge mass in between from simulation also confirmed that allowed for an increased shear signal. So this was the idea. You see a lot of different colors because this is a really fully multi-wavelength experiment, because we have measurement with Merlin, measurement coverage with VLA in the radio, Subaru, Spitzer, GMRT, and Scuba. So to do really a multi-wavelength analysis. Why do we need Merlin when we have already VLA? Well, this is shown in this plot here, where you see the number density of baselines as a function of the length in meters of the baselines. And JVLA is in blue, where Merlin is in pink. And overplotted is the shear, the shear signal that we expect in that region for the sky from simulation, and what are the scales at which it peaks. And as you can see, using only JVLA, we were going to miss the peak of the shear signal. So the increase due to Merlin baselines was going to be crucial. At the moment, as I was saying, the density of sources was very low and the area was small. So this allowed for the detection of the optical shear signal due to radio galaxies detected in the optical. This is the left-hand side plot, so the EE power spectrum of shear. But we didn't manage to have a detection either in radio optical or radio. But this was just the first test, because the second observation season for superclass is already ongoing. I mean, is already done, and now data is being analyzed. And this is going to be important, and this is my last slide, because of the following here. This is a courtesy from Ian Harrison. You see a kind of Moore's law of the total number of galaxies with shear ellipticity estimates that we have as a function of the year of the survey. And the blue line, well, you can see definitely a kind of Moore's law for the blue points, which are optical surveys. You see Combo 17, AHST, CFHT lens, KIDS, Dark Energy Survey, W1st, Euclid, and LSST in the future. Whereas for what concerns the radio, well, in the radio we have VLA first, which is really off this Moore's law, and then superclass. And on the way up there, there's SKA. So basically, we need to prove with superclass that this is feasible to have observation time with other experiments, with other facilities to bridge this gap. Otherwise, we won't be able to have ready pipelines for what the SKA will be ready. And with this, I think that I would thank you for your patience, and I think I'm finished.
Thank you so much, Stefano. We have a few minutes for questions. Mike?
Yeah, I think you answered most of my questions about the radio continuum survey in the south, RACS. A little one slide, but I was curious. It covers a lot of sky, right? And it goes way up into the north. And the NVSS goes into the south quite a way, if I remember. So
yeah,
are they very different frequencies, or what's the reason for so much overlap? Because if you just wanted to plug the whole you wouldn't need to do so much, I guess.
Right. So it's frequency are slightly different because MVSS was mostly 1.4 gigahertz, if I'm not mistaken. But the overlap is very big because it's basically the other way around, it's just flipped. But yes, this RAX was basically the first survey that was going to be done, but the real aim is what is called EMU, which is the evolutionary map of the universe, which is a planned, well, it's already ongoing. We have already data for the first science verification, which is a 3/4 of the sky survey, radio continuum, much deeper than that. So RAX was very fast in scanning the whole sky. Is still the deepest in the radio in the southern hemisphere, but is not very deep. But the aim is to do something that is really also useful for cosmology, for standard cosmology, and that is going to be EMU.
Any other questions? If you, before the eMerlin, if you go to the one you were talking about before, it seems like you're measuring the cross correlation. If you keep going back, get previous slides.
For eMerlin, I mean, this plot?
No, not for eMerlin. The one before, I forgot the name.
Ah, Meerkat.
Yeah, Meerkat. What is the, so how far are you from measuring the autocorrelation for that instead of just the cross correlation?
We're getting closer, I can tell.
Okay.
Well, we're learning a lot. We're learning a lot because really the issue is foreground removal. And the point is that modeling of foregrounds is still not mature enough. Because if you look like a state-of-the-art simulations of foregrounds, like all kind of agree that when you use PCA or some sort of stuff, but just think of PCA, you converge. So you stop removing foregrounds and you like reach a plateau where it's just signal after you removed order of a few modes, let's say up to 5 modes or something like that. These measurements that have been done so far, so the one that I listed back here, all removed at least 20, if not 30 foregrounds, meaning that there are many more contributions to the total foreground contamination than those that we know at the moment. So by doing this like pathfinder experiments, the aim is also to understand much better what's going on and what are the best techniques. So instead of PCA, we recently started using also other approaches, GMCA, independent component analysis, Gaussian processing, etc. And basically what you see is that you really have complementarity between them to reach the best, if you want to remove the foreground. Another approach is what they do, for instance, in CHIME, which is foreground avoidance, so just trying to look at the area of the K parallel, K perpendicular space, which is not contaminated with foregrounds. But this cuts out some of the scales that might be interesting, like the larger scales.
And so have people, I understand that there are these difficulties with the foregrounds, but have there been attempts to put upper bounds to what the signal could be?
Yeah. With the autocorrelation, there are upper bounds at the moment, yes.
And how far are those upper bounds from the theoretical expectation of what's
it's still more than an order of magnitude, yes.
Okay. Thanks. Any last questions for Stefano? The smell of the pizza is strong, so I think we should leave there. Then thank you so much, Stefano. We really appreciate this.
Thank you again for
Hope to see you in person. All right,
yeah.
bye.
Thanks.